So in this video, we're going to talk about the divergence theorem. So this is going to follow in the same pattern as most of the main theorems we've been talking about lately. So let's just refresh our memory on some of the same slides we saw when we did Stokes' theorem. So let's recall the fundamental theorem of calculus from Calculus 1. Remember, we phrased this as if we take the derivative or the integral of a derivative of a function over some interval, the only thing that matters is what's happening with the function itself at the boundary of the interval, so the edges of the interval. So the integral of the derivative completely determined by the boundary of the region. And then we saw the same thing if we looked at the fundamental theorem for line integrals. In this case, for our derivative, we used the gradient of f, and then that gave us a vector field. So we took the line integral of that, and we saw the only thing that mattered in this case, again, was the boundary of the curve, which are just the beginning and end points of the curve. So again, this is a type of derivative, and the fundamental theorem of calculus from Calc 1 is just a special case of this. So then we moved into Stokes' theorem, where now our region of integration was a surface that was bounded by a boundary curve C, and we assumed that the orientations on S and C agreed. Then we saw that if we look at the integral of the curl of f, so another type of derivative, and we integrated that over the entire surface, all that mattered was what was happening with the vector field f around the boundary of the surface, which in this case was a curve. So we reduced the integral of a derivative down one dimension again from a two-dimensional surface to a line integral, so just a one-dimensional integral. So what we want to do now is move up one more dimension. And of course, you can keep moving up higher and higher dimensions with this, but we're going to stop at 3 dimensions for this course. And so in this case, we're going to take a region in 3 space, so a solid in 3 space. And so then the boundary of that solid is going to be just a surface. So we're going to want to relate the integral of some kind of derivative over the entire 3-dimensional region to the integral on just the boundary of the surface, or of the region. So this is going to be what the divergence theorem is, and so it's going to look just like the theorem we just had, but of course we have to figure out what the correct derivative is in this case. In this case, it's going to be what we call the divergence of the vector field, hence the name divergence theorem. So let's go ahead and define our divergence. So thankfully, the divergence is actually much easier to calculate, less work to calculate at least, than the curl of a vector field, because in this case, we're essentially taking like a dot product instead of a cross product. So you can use either notation here, either div f for divergence of f, or more suggestively, this nabla here, this del operator dotted with f, because if we think of the del operator there as partial derivative of x, I, partial derivative of y, j, partial derivative of z, k, and then we kind of apply that through the dot product to our functions, we get the partial derivative of p with respect to x, plus the partial derivative of q with respect to y, plus the partial derivative of r with respect to z. So you can see this is pretty easy to calculate. We're just taking 3 partial derivatives and adding them together. The other thing to notice here is this is a scalar that we get out of this. So when we took the curl, we got a vector out of it. In this case, we just get a scalar. And so what this divergence measures is kind of how much our vector field is spreading out. So we're going to illustrate this with several examples of vector fields we have already looked at, and then maybe another new one as well. So let's start with this vector field. So we can think of it as a vector field in 3 space, but we'll just look at it in 2. So we just have xi plus yj. So if you remember, this in 2 space was just this vector field, where all the vectors were kind of pointing away from the origin, and they got bigger as we went out. So if we think of this, this does seem to be spreading out. So we would expect this to have some kind of positive divergence if the divergence is really measuring how much the vector field is spreading out. And we can see that's the case. We just get 2 here, because in this case, p is x and q is y. So the partial derivative of x with respect to x is 1. Partial derivative of y with respect to y is 1. So you just have 1 plus 1. And there's no r component here, so that's just adding 0 to it. So we see this does have a positive divergence of 2. This was another one of the vector fields we looked at. So if we recall this one, this was just vectors circulating around the origin. You just think of this as if we drop something into the water here, it's just circling the origin on circles here. And the further away from the origin, the stronger the current kind of is here. Now, this one doesn't seem to be spreading out at all. It's just circling around. And as you can see, the divergence here is 0 because the partial derivative of negative y with respect to x is 0, and the partial derivative of x with respect to y is 0. So there is no divergence, which is exactly what we would expect here. So now let's take a little bit more complicated of a vector field. So let's take our f here to be cosine of xi plus sine of yj. So this looks something like this for the vector field. And we can see there's a lot going on here. In some places it looks like it is spreading out, in some places maybe it's not spreading out. So if we calculate the divergence of this, we get negative sine x plus cosine y. So this vector field is going to have differing divergences at different points x and y. So that's perfectly fine for a vector field to have. If it's a complicated vector field, the divergence can be different everywhere. And finally, one more example in 3 space. So if you remember this one, this was just the rotating vector field that we saw earlier, but then we also added a z component to it. So while it was flat and just rotating in the xy plane, as we increase z, it starts to rotate upwards more. So it's kind of rotating, it's kind of spiraling upwards as it goes. So it does seem to be spreading out some, because if we think of putting a particle in there, it's not going to just go around in a circle and come back to the same spot. It's going to spiral upwards. And as we can see, if we take the divergence of this, we get 1 because the partial derivative of negative y with respect to x is 0, plus partial derivative of x with respect to y is 0, but then the partial derivative of z with respect to z is 1. So this has a positive divergence. And so finally, the divergence theorem we can state now. So we're going to let V be a subset of 3 space, which is bounded and has a smooth boundary surface. We're going to orient S, so since it's bounded and it has a boundary surface, there's an inside and an outside to this. So we're going to orient our surface so that the unit normal vectors point outward from V. So we'll see a picture of this on the next slide. And so if we have a vector field that satisfies all the partial derivatives of P, Q, and R exist and are defined in a neighborhood of V, then if we integrate over the entire 3 space of the divergence of this region, so we integrate over our entire 3-dimensional region V, and we integrate the divergence, that's a three-dimensional integral, so a triple integral there. All that matters is what's happening on the boundary S, and we just get a flux integral back. So same type of setup as we had before. Now we do have to be very careful with this in that there are some very important vector fields that are not always defined everywhere. So for instance, if we think of the vector field due to gravity, that's not defined at the origin, though we might want to think of a region that includes the origin. So we have to be careful that we can't necessarily use the divergence theorem then, because our partial derivatives don't exist in the entire area of V. There's a spot where they're not defined. So here's a picture of a surface and what we mean by orienting the normal vectors all going outwards. So this is like a donut shape. It's called a torus. And you can see all of the normal vectors are pointing outward from the inside of the surface. So the region V would be the inside of this donut, and you can kind of think of the surface as like the icing on the donut. So we'll see lots of examples in class of how to use the divergence theorem to simplify some integrals, and we'll see at least one really cool example from medical imaging.